So we continue with our optimization problems, and for this example, it's about nutritional backpacking. So this problem states, a backpacking outfitter would like to meet certain daily nutritional requirements for its freeze-dried food packages and keep the overall weight of the packages to a minimum. The requirements call for 20 units of carbohydrates, 15 units of protein, and 15 units of fat. The outfitter is considering a combination of two food packages. A night package weighs 2 pounds and contains 4 units of carbohydrates, 2 units of protein, and 1 unit of fat. A morning package weighs 1.5 pounds and contains 1 unit of carbohydrates, 1 unit of protein, and 3 units of fat. Determine the optimal solution for the number of each type of package that should be supplied to a backpacker and still meet the nutritional requirements. So we can see right here that the objective function is going to represent a minimum. We have it right here. For this chapter, if problems are going to be representing maximums, we've been using the variable p, but since this is a minimum, we're going to use the variable c. Now, even though that we're trying to keep the weight right here to a minimum, we're still going to use c. We're going to let c designate a minimum that's trying to be attained. So since the weight is our objective here, we can see that a night package, I'm just going to go like that, our night package weighs 2 pounds. And then a morning package weighs 1.5 pounds. So if we let X represent a night package, then our weight can be 2X, 2 pounds for the night package. And if we let Y be the morning package, then we have 1.5 Y. So this is the objective function for this problem. So now that we have that, the next step is we'll go ahead and we'll build our table. And we could see right here, determine the optimal solution for the number of each type of package. So the packages again are the night and the morning. So those are going to be our variables. And we know that the variables go across the top of our table. They're going to create columns. And then the rows, those are the elements that are associated with the variables. And those are carbohydrates, we could see right here, protein, and fat. Also keep in mind that the totals are also going to be within our rows there. And we could see here we have 20 units of carbohydrates, 15 units of protein, and 15 units of fat. So now that we have all the elements needed to build our table, the table should look something like this. So again, here we have our variables at the top, those that are going to fluctuate at the top of our table, creating the 2 columns. Here are the elements that are associated with them. Again, we have another column here. We just happen to label it with the totals here. But right here, we have our objective function. Of course, we have it listed as weights here, but we use the variable c. And again, the reason we have this is we want to show the association between the weight and the number of night packages and, of course, the number of morning packages. So now that we have our table, we can see right here that that's going to be our system of equations. So we'll go ahead and we'll write that down. For x, x being the night packages, plus y, that's equal to 20. 2x plus y, y of course being the morning packages, that's 15. And then x plus 3y, that's also equal to 15. And we'll close off that system. Now that we have our system of linear equations, we can go ahead and we can graph it. Now again, your graph doesn't have to be anything fancy, just something clear enough so that it models the scenario here. So it should look something like this. Now this graph looks a little bit different than the ones we've created before, because now we're looking for a minimum. So here we have the line 4x plus y is equal to 20. Here is 2x plus y is equal to 15. And of course, here is x plus 3y is also equal to 15. But again, since this is a minimum, the requirements call for 20 units of carbohydrates. So we can have more than that. There could be more than 20 units. There could be more than 15 units of protein. There could be more than 15 units of fat. So as long as it has at least 20 units. But of course, we want to keep it to a minimum, yet still meet the nutritional requirements. So now we'll write our system of linear equations that's going to properly model the constraints of our objective function. So it'll be 4x plus y, but it's going to be greater than or equal to 20. 20 is the minimum. It could be more than that. 2x plus y greater than or equal to 15. This would be our protein. It could be 15, but it could also be more. And then x plus 3y, that's greater than or equal to 15. That represents our fat. We could have more than 15 units of fat. So this is the minimum. Again, we're also going to put in x is greater than 0. If x represents the night packages, and y has got to be greater than or equal to 0, and y represents the morning packages, we do that because we can't have negative packages. So this are the constraints for objective function here, and I'm just going to write it in right here. So here we have our objective function, it's a minimum, and here we have our constraints. So then our feasible set, all the overlap for our inequalities here is going to be bounded this way. We have a point here, we'll have one here, we'll have one here, and then a final one here. So it looks something like this. Everything going that way. Here, 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 and then off this way. So our feasible set winds up going off in this direction. So I'm just going to write it in here. And again, any coordinate out here will satisfy our inequalities here, but we don't want any one. We want the one that'll give us the minimum one. So this coordinate right here, this point right here, we have the line 4x plus y is equal to 20. This is a y-intercept that happens when x is equal to 0. So when x is 0, y is going to be 20. Then if we go down here to this one down here, here is the line x plus 3y is equal to 15. That has an x-intercept that occurs when y is equal to 0. So then this is going to happen at 15 and 0. So now we have this coordinate that we have to find, and of course this one. So this one, this is where 2x, right here, 2x plus y is equal to 15, intersects with this line right here, 4x plus y is equal to 20. So if we put down 4x plus y is equal to 20, then we write this in slope-intercept form. Y is equal to negative 4x plus 20. Then we do the same for this line here. 2x plus y, that's equal to 15. Slope-intercept form, y is equal to negative 2x plus 15. To determine the coordinate, we'll make these two equal to each other, solve for x, and then use that x to help determine y. So we have negative 4x plus 20. Make that equal to negative 2x plus 15. We can add 2x to either side and then subtract 20 from either side. So we'll have 2x minus 4x. That's going to be equal to 15 minus 20. 2x minus 4x, that's negative 2x. 15 minus 20, that's negative 5. So x has got to be 5 halves. We then take this value and slug it into either one of these. If we slug it in down here, -2 times 5 halves, that's -5, and -5 plus 15, y is equal to 10. So the coordinate for here, 5 halves and 10. We do the exact same thing for this one down here. So we have this line here, 2x plus y is equal to 15. We write that in slope-intercept form. Y is equal to -2x plus 15. And that intersects with this line down here. X plus 3y, that's equal to 15. Y is equal to -1/3 x plus 5. Make these two equations equal to each other. Solve for x. Use that x to determine y. -2x plus 15. That's going to equal to -1/3 x plus 5. We can add 1/3 to either side and subtract 15 from either side. That'll give us 1/3 x minus 2x. That's going to be equal to 5 minus 15. 1/3 x minus 2x, that's -5/3 x. 5 minus 15, that's -10. X has got to be equal to 6. Take this value and slug it into either one of these equations. How about if we slug it in here? -2 times 6 is a -12. -12 plus 15. Y has got to be equal to 3. So the coordinate for right here, 6 and 3. So then the final step, the third step, is to go ahead and we have to check each one of these within our objective function. So we'll do that. So C is equal to 2, using this coordinate here, 2 times 0, plus 1.5 y, and y is 20. 1.5 times 20, that's 30. And since we're looking to minimize the weight, that's 30 pounds. We'll try this one here. 2x, and that's 5 halves, plus 1.5 y, which is 10. 2 times 5 halves is 5. 1.5 times 10 is 15. 5 and 15, that's 20. Again, this is pounds. We'll try this one here. 2 times x, which is 6, plus 1.5 times y, which is 3. 2 times 3, 12. 1.5 times 3 is 4.5. 12 and 4.5, that's 16.5 pounds. And then finally we have 2 times 15 for this last coordinate, plus 1.5 times 0, and that's 30 pounds. So since we're looking to minimize, the smallest value here is right here, 16.5 pounds. So determine the optimal solution for the number of each type of package that should be supplied to a backpacker and still meet the nutritional requirements. So the outfitter should supply a backpacker with 6 of the night packages and 3 of the morning packages. By doing that, the backpacker will get the required nutritional output, but yet keep the weight to the food packages to a minimum. And there we go.